Howdy everybody, welcome back to Urban Odyssey. This is going to be part 9, section 9 of the 6G white paper walkthrough. This one is the Internet of Space, Things, and CubeSats. Stick around, guys. Alrighty guys, we have some words and terms for you again. Let's get those here. There you go. Let's see, it's the last one. The very first one is the Internet of Space Things. This is the Skynet itself. It is a cyber physical system spanning ground, air, and space. It integrates the Internet of Things, basically surveillance devices, with CubeSats and UAVs to guarantee global coverage for data harvesting and command and control of human nodes. It eliminates gaps in the control grid. Next, we've got CubeSats. These are the swarm. They're miniature satellites, around 10 by 10 by 10 centimeter units. They're cheap, disposable, and easily reconfigurable. They form mega constellations like Starlink to create a dense, inescapable mesh of surveillance eyes in low Earth orbit. They act as the relay nodes for the kill chain data. Unmanned aerial vehicles, UAVs. These are drones and enforcers. Autonomous aerial assets used for data aggregation and relaying signals in the context of omnivore. These are platforms for lethal autonomous weapons warfare systems, laws, loitering over populations to dispense wireless justice or harvest biometric data from the wireless body area network. We have GSL, ground to satellite links. This is the upload and download, the connection between the terrestrial controllers or the human targets on the ground and the orbital overlords. This link facilitates the exfiltration of biodata and the download of behavioral modification algorithms. ISL, inter-satellite links, the orbital mesh, communication links between satellites, CubeSats, allowing them to talk to each other without touching the ground. This creates a network in the sky that is resilient, self-healing, and difficult to disrupt, ensuring the control grid survives even if the ground stations are destroyed. Heterodyning, frequency alchemy, a signal processing technique used in transceivers to mix frequencies, such as mixing optical and light signals to generate RF. It allows the system to convert light-based control signals into radio frequencies that interact with the human biofield. And finally, stateful segment routing, SSR, the predatory path, a routing protocol that tracks the state of the network in real time. It allows the grid to dynamically reroute kill signals or surveillance streams around obstacles or failures, ensuring the packet, the weaponized data, always reaches the target. All right, that is all of the words and terms. So let's go ahead and get into the reading. Let me highlight my cursor there. All right, guys. We're almost done with the paper. We've got just a few more sections, and that will be it. And then we can say that we have read it. And whenever you go and talk to people about these subjects, you can tell them that you have read a lot of the paper because you've watched my videos. And then you can show your friends my videos. I highly encourage you to, if you're trying to educate people about these topics, send them my playlist, my channel. feel free to have them ask questions. I'm always happy to answer questions as long as people are just nice and respectful. I mean, if you disagree, that's fine. Just please be respectful, and I'm always open to open conversations around these things. So, all right, let's get started. Section 9. The Internet of Space Things with CubeSats and UAVs. The Internet of Space Things, the IoST, is a spatial expansion of the Internet of Things, which primarily focuses on terrestrial use cases for future communication networks. This expansion is necessary for the following reasons. One is that the Internet of Things relies heavily on existing infrastructure and hence lacks flexibility as well as scalability. 2, global coverage is impossible using traditional Internet of Things solutions, especially in remote areas including the North and South Poles, due to the imbalance of construction expenditure and service revenue. And 3, limited heterodyning and spectrum resources in the Internet of Things network. Let me see. Yes. Okay, let me show you figure 10. I've got it here for you. Here you go. This is figure 10. It is the illustration of the Internet of Space Things. To this end, the Internet of Space Things is envisioned as a ubiquitous cyber-physical system spanning ground, air, and space with applications in monitoring and reconnaissance, and space backhauling and holistic data integration. More specifically, as shown in Figure 10, the Internet of Space Things consists of the ground station, customer premises, and on-Earth sensing devices, which form the ground segment in the CubeSats, UAVs, and near-Earth sensing devices that form the space segment. The ground-to-satellite links connect the Internet of Space Things hubs with CubeSats to exchange requests and data, and the inter-satellite links relay information to neighboring CubeSats in both the same orbit as well as adjacent orbits. Further, the UAVs establish links with each other, as well as sensors and CubeSats, to form a localized data aggregation layer. To this end, we note that UAVs are expected to feature heavily in the upcoming 3GPP releases 16 and 17. Further, since the space segment forms a vital component of the system, research relating to the development of small satellites or CubeSats for use within the Internet of Space Things is of critical importance. Now, again, I like to remind people, if you are new or you're just watching this episode, this paper is from 2020. And so if you use hindsight, which is always 2020, and that's an irony right there, a pun, it was not intended. But if you look back from where we are today, this is really that whole push for Elon's Starlink. It's why he's getting all of these government CIA contracts, making a lot of money, because they probably are taking this 2020 information here, and over the last few years they have been trying to contract the work out to accomplish the things we're reading about. That's just my guess. I can't, I don't have any evidence for that, but that's just kind of what comes to mind when we read this. CubeSats are a set of miniaturized satellites with sizes ranging from 1U to 6U, with a U being 10 by 10 by 10 centimeters cubed. Let me show you all a picture of a CubeSat, because I think it will help. So this right here is a CubeSat. That's what a CubeSat looks like. I don't know when that's from. That might be an older model, but that's what they look like. Okay, 1U to 6U, with the U being the base, 10 by 10 by 10 centimeters cubed. Currently, CubeSats are being deployed for a variety of applications, including Earth sensing, positioning, and the Internet of Things, and machine-to-machine communications. Compared to traditional LEO, low Earth orbit satellites, CubeSats present a number of advantages relating to one, lower cost and shorter development cycles. That's figure 11, conceptual design of a next generation CubeSat. 1 second. There you go. Figure 11. Two, it has higher flexibility and scalability. Normally, the development cycles range from 3 to 7 years for traditional low Earth orbit and geographical Earth orbit, I think, satellites, and the costs are extremely high. Also, since the payloads are predetermined in the LEO and GEO satellites from the period of development to until deployment, it is difficult to reconfigure any component in the middle of the process. However, CubeSat's development can be done in a remarkably shorter time than COTS components with much lower cost. This also guarantees that CubeSats are easily reconfigurable. This is all about programmable matter, and I hope you guys have kind of seen that as we've been going through this. The idea is that they want as much control over matter as possible, and so to do that you would essentially fill it or pack it with these nano-sized dust programmable chips. They are nano-sized dust chips that can be programmed. They proposed a new next-generation CubeSat hardware concept, and that's what Figure 11 was. The proposed CubeSat design includes an all-new communication subsystem for seamless operation and a wide variety of frequency bands. More specifically, the novelty of the design concept is characterized by the presence of multi-band transceivers and antennas that are able to support wireless communication at microwave, millimeter wave, and terahertz frequencies, as detailed in the following section. Through this unique CubeSat design, we can potentially achieve data rates in excess of 100 gigabits per second. Also, I wanted to let everybody know on the spectrum first, at the, I guess it would be the the smallest would be the microwave, and then you would have millimeter waves, and then you would have terahertz frequencies. And I've got figure 3, which I will include in the Substack post if you want to see that visually. Okay, so subsection A, multi-band communication subsystems. The primary motivation for a multi-band communication subsystem comes from the fact that existing CubeSats have limited communications capabilities, largely relying on spectrums ranging from the L-, which is 1 to 2 gigahertz, till the Ka-, which is 26.5 to 40 gigahertz band. There are two major drawbacks associated with this approach. First, the traditional frequency bands are becoming increasingly prone to congestion. Second, the terabit per second level throughput required by the Internet of Space Things cannot be achieved with existing frequency bands as of 2020. Probably, and if I had to guess, the military has already solved this problem, but if we're to assume that this paper is going to, like private partnerships and whatnot, this is not classified government research, obviously. They're probably trying to bring that technology from the military industrial complex sector into the corporate making money on it, making it private business model. To overcome the spectrum scarcity and capacity limitations in current satellite networks, we have proposed the use of multiple frequency bands from the RF to terahertz spectrum. In the Internet of Space Things, the use of such frequencies has been made possible by advances in high-frequency device development by aforementioned military research. more specifically, as part of the multi-band communication subsystem, we have developed both multi-frequency transceivers as well as antenna subsystems, as described next. As shown in Figure 12, in our multi-band transceiver, we use two complementary approaches, namely an electronic frequency up converting chain and an optical frequency down converting chain. Let me show you Figure 12. That is Figure 12 there. You zoom in on it. They're using electronic frequency up converting chain and an optical frequency down converting chain to generate signals at different frequencies. With regard to the electronics-based approach, the primary idea is to use frequency splitters in order to extract the intermediate frequencies for outputs. For example, as shown in Figure 12, the signal at frequency F1 is considered as the intermediate output when producing signals at a higher frequency F2. I think that's on the next page, yeah. There's F1 and there's F2. I don't fully follow this as much as I would like, but if anybody has more understanding of this, please do feel free to let me know. On the other hand, the photonics-based approach involves the down conversion of optical signals. As shown in Figure 12, multi-band signals are generated by heterodyning two input signals with a Mach-Zehnder modulator. The resulting RF signal has a frequency equal to the difference between the two inputs. The generated signal, along with the two input signals, serves as the final output, distinct from the commonly used up conversion and down conversion techniques where intermediate frequency products are abandoned. Our approach harvests them and utilizes them as a part of the multi-band communication system. So they're very, open. Let's see. Our approach harvests them. Yeah. So they absolutely are for energy harvesting. Their papers say that, and we are going to go over more white papers that are a bit just more blatant than this one, if that's possible. So they harvest your energy and utilize that as part of their multi-band communication systems. These multi-band frequencies can be assigned to the GSLs and ISLs dynamically to accommodate various service requirements. To this end, within the Internet of Space Things, the GSLs make use of the more robust microwave and MM frequencies, while high-capacity terahertz links form the ISLs. Let's see, let me bring these back up for you. GSL, ground to satellite links. Inter-satellite links, ISL. In addition to multi-band transceivers, CubeSats in the Internet of Space Things are also equipped with multi-frequency antenna systems. In particular, as discussed in Section 3, in the use of terahertz links allows for very large antenna arrays that serve as the basis for massive MIMO, which means multiple input, multiple output, and ultra-massive MIMOs, communication schemes. More specifically, we note that there exists multiple options when it comes to the design, of multi-band antennas arrays. The first approach involves the use of NEMS and MEMS, which are nano electromagnetic systems or mechanical systems. Nano electromechanical systems, and then MEMS is micro electromechanical systems. There are so many acronyms, and that makes this just so much more complex because in addition to having to learn a whole new grammar set to understand this, the grammar set doesn't consist of words, it consists of acronyms, which are multiple words put into like one word. So, and that's why I've built the table. Here, let me show you that real quick. This is the table, and I have this handy in case we ever need to reference it. So, like for instance, right now, if I was to go to the table and go and search MEMS, and I was to scroll down right there, you will see. Okay, I went ahead and played with that a little bit and made it a little bit easier to view for everybody. So let's see, let's go. There's MEMS and there's NEMS right there. So MEMS, and this is, you can find the link in the description, the spreadsheet directory that I've been adding to as I encounter these new words and terms. I put them into this spreadsheet so that people can have access to it. So MEMS, micro electrical mechanical systems. Basically, smart dust is probably NEMS, the nano scale sized particles. So please make use of this. I really think it will help people who have a hard time with the words and terms. Okay, so the first approach that they talk about uses NEMS or MEMS and the origami structures to create physically reconfigurable antennas, wherein the size of the radiating elements can be changed physically with a view to adjust their resonant frequency. On the other hand, the second approach proposes the use of materials such as graphene to create electronically tunable nano antenna arrays. So here's graphene popping up again, and there's a lot of things about graphene, especially when you're talking about human husbandry. Graphene is probably part of the heavy metals that are being sprayed. There's aluminum, strontium, barium, graphene. There's a lot of different ones, and the whole weather modification thing. A lot of people talk about the weather modification, and that is definitely a real thing, but it's more or less the way that they're doing it is what this paper is talking about. So the idea of having these programmable NEMS and MEMS and MIMOs, they can actually use that to modify the weather. And that's kind of the thing that's going unsaid. And so the weather modification is absolutely real. It's just being done with the same technology that's being used for human husbandry. So in this case, the resonant frequency can be controlled by modulating the graphene Fermi energy or chemical potential. This allows for the tuning of the antenna to resonate at different frequencies without physically changing its size, in contrast to the MEMS-based approach. Subsection B, System Constellation Design. Within the context of the Internet of Space Things, an ideal constellation design is crucial to achieve true global coverage and satisfactory link performance. However, conventional LEOs, which is low Earth orbit constellations, are typically characterized by the presence of fewer than 100 satellites. For example, the CubeSat-based Internet of Things system, Astrocast, has a maximum of 64 satellites. At the outset, the coverage and connectivity offered by such systems leaves much to be desired. motivated by the need for improved coverage, reliable connectivity, and increased redundancy. Mega constellations of several hundred satellites have gained significant traction over the past year, and then enter in the contracts given to Starlink and whatnot, is what I kind of was talking about earlier. So, yeah, mega constellations provide several advantages over traditional constellations, including but not limited to increased coverage density, improved connectivity, and higher redundancy. More specifically, constellation design typically involves solving for several interrelated parameters, such as 1, the apogee and perigee radii; 2, the orbital eccentricity; 3, the number of CubeSats per orbital plane; 4, the number of orbital planes; and 5, the initial longitude of the ascending node. Argument of pedigree in the true anomaly of CubeSats. While a fairly challenging problem in itself, the presence of an extremely large number of satellites further serves to complicate the system design. Consequently, the existing state-of-the-art constellation design frameworks are largely geared towards the design of systems with a few dozen satellites at best. To this end, we have proposed a highly scalable and customizable constellation design framework that takes into consideration both coverage and connectivity parameters. Through the use of novel metrics such as spherical Voronoi tessellation based coverage characterization. These words are tongue twisters, and I feel like they're just, it's like they write it like that on purpose. Yeah, spherical Voronoi tessellation based coverage characterization. Say that 2 times fast. And ISL, man, I keep drawing a blank. Let me get what that stands for. Inter satellite links. ISL's inter satellite links. Feasibility based connectivity parameters. We are able to demonstrate that the resulting IoST, Internet of Space Things constellation, achieves a performance level that is similar to existing state-of-the-art mega constellations such as Starlink. There it is. While requiring only a quarter, i.e. less than 500 of the satellites. And I think the final subsection here is C, network management. The Internet of Space Things encompasses a vast infrastructure spanning both the Earth as well as space. A complex network of this kind has much to benefit from fine-grained real-time control that is well suited for tackling the peculiarities of the space environment, namely temporal topological variation and long delays. Going beyond the traditional bent pipe nature of satellite communication systems, the Internet of Space Things makes extensive use of SDN software delivery networks and network function virtualization to significantly improve network resource utilization, simplify network management, and reduce operating costs. In a manner similar to the infrastructure as a service paradigm, the Internet of Space Things intends to deliver CubeSats as a service. That's important. I don't necessarily know what that means, but I would kind of go to Starlink again. But please be aware that Starlink is not, absolutely not the only company doing this. But I do believe that Elon Musk has enough money that he can make his business kind of take the, be in the front of the line. So, I mean, people want to do business with billionaires and trillionaires, or however much money the guy's got now. It's more money than you and I would know what to do with. In particular, we have demonstrated that through the use of SDN software delivery networks, it is possible to achieve a sub-second end-to-end latencies. That's pretty crazy. More specifically, within the domain of network management, the Internet of Space Things introduces the novel concepts of virtual CSI, VCSI for joint optimal physical link layer resource allocation, and stateful segment routing for overcoming challenges associated with the high latency space segment. In particular, concerning the latter, which means stateful segment routing, the Internet of Space Things extends the traditional software delivery network paradigm by including support for state-based, meaning state-based is like kind of holding variables or holding data. Again, a state, if you log into a website, in the programming of the site, the state would hold information about your username and your email, and it would have a link to your profile image so that it could display that. That's what a state is. By including support for state-based packet forwarding that takes into account the topological configuration of the network at any given instance of time, while the use of segment routing helps in the minimization of control traffic, in addition to a higher level of demand, satisfaction, and load balancing as demonstrated in 152. Further, the Internet of Space Things also employs predictive algorithms to preemptively detect GSL outage events, which, when coupled with gateway diversity, result in the realization of proactive handovers that minimize handover interruption time. In addition, the Internet of Space Things proposes the use of containerization in CubeSats for achieving lightweight hardware virtualization without significant overhead. I think containerization, if you have any, if you've ever done programming, it's like Docker containers. Basically, I can package up my software as a container, which means it has all of the, you don't have to install it to your device. It is for instance, a Linux that already has it configured. It's like installing Windows as a container. If you don't really have the background, then it's probably harder to understand. That's just my guess, though. And in CubeSats, containerization in CubeSats for achieving lightweight hardware virtualization without significant overhead. Going forward, we note that the aforementioned techniques will play a vital role in the realization of pervasive cyber physical systems of this kind. One thing that came to mind that I will leave you with for those of you who've made it to the end of the video. This is interesting. Let's see. Packet forwarding right there. Packet forwarding. You wouldn't believe it if I told you, so let me show you. So you wouldn't believe it if I told you, but packets are data, and there is a software called Archime with their nice owl logo there, but they did change their name because people started wondering, what is the Verizon Moloch conference? And turns out that it was the name of this software. It was called Moloch. And I mean, I guess that's just something you might name like your software, I guess. So Moloch is a open source, large scale, full packet capturing, indexing, and database system. So it's just huge spyware for internet data. And this one's by Visa, so it's probably in use by Visa. Archime, that's their new name, because people they probably couldn't get away with that. But let's see if I can find the original. Here it is. Perfect. What about that? I told you, you wouldn't have believed me if I told you. This is just crazy. So internet data, packet capture, database searching, and the name is Moloch, and you have the Verizon Moloch conference, and now they've changed their name but kept the owl logo. So for those of you who finished the video, now you know something new and strange. Take care, guys. We'll see you in the next one. We're almost through. We're almost done with the paper. For those of you who have stuck with me this long, kudos to you, because this paper is a drag. Take care.